Welcome to part 2 of this mini-series key tutorial on the topic of MPLS. Today we're going to look at what MPLS TP is all about and how it works really well as a carrier grade transport technology. Now, you'll remember that in an MPLS network, a fixed label switched path, or LSP, is first set up between two end nodes called label edge routers, or LERs. And in the model on the diagram, the path carries a pseudo wire from the input of one provider edge device to the output of the similar device at the far end. And any native data from the customer can be carried over this pseudo wire. And last time we saw how MPLS was a really great way to carry packets because each packet is simply given a label on ingress, and then it rapidly makes its way through the network, being forwarded just according to its label. At each router, its label is read and removed, and it's given a new one before being transmitted onwards. And the job of reading and switching labels is really quick compared to routing processes. So MPLS transmission has very low latency. And we also said last time that MPLS doesn't care really about which underlying technology is carrying it. So, in this session I want to look at how MPLS has had to develop to meet the needs of metro, aggregation and access networks so that it's equipped to provide a suitable replacement for traditional transport infrastructures. Put simply, if MPLS is going to be up to the job, it has to be as good as, if not better than, traditional circuit-based technologies like SDH. Now, interestingly, traditional operators actually liked quite a lot about MPLS, or IP MPLS to give it its full name. But for them to adopt it, there needed to be quite a number of improvements in key areas which would be essential for carrier class connection oriented transport, such as protection switching and OAM. But secondly, there needed to be some of the basic features of IP MPLS that had to be dropped, like penultimate hop popping, and we'll look at why in a minute. But to cut a long story short, the result was a new type of MPLS called MPLS TP, with an architecture that is predictable, with bidirectional paths, that is deterministic and resilient. MPLS TP started life in 2008, exactly 10 years after the original MPLS was launched, and it was the ITU-T and the IETF working together on the project. Actually, the ITU-T had worked alone the previous year on an aborted version called TMPLS. Now, the TP stands for Transport Profile, but what we need to be clear about is that MPLS TP is not a subset of IP MPLS. It's more like the son of IP MPLS. It stands distinct from IP MPLS, but is related. MPLS TP has the DNA, we could say, of IP MPLS. And importantly, it is compatible with IP MPLS, which the ill-fated TMPLS was not. So, what are the key themes of this new technology? Well, we have the speed of MPLS, that's there, but so is the rock-solid dependability of SDH. And for monitoring and maintenance, we've got a toolkit of features available, but we avoid the ever-increasing costs of having to maintain a classic circuit-oriented infrastructure. One of the drawbacks of IP MPLS is that you just can't guarantee that the return path will follow the same route as the outgoing path. It's what we call non-congruent. So why is that a problem? Well, let me explain it with an illustration. Imagine that you're going on a road trip from Paris to Rome with friends. You go first in your car, and they're going to follow along later. So you pass through a number of cities, and you eventually come to Florence. But as you passed Genoa, you noticed that the city workmen are beginning some roadworks that will block the roads in and around Genoa for some time. Your friends have now begun their journey and are on their way to Turin. You want to contact them to tell them about the roadblock and that they should make a detour via Milan. But the bad news is you live in a non-congruent world, and you are only able to leave messages for them to collect at points on the return path, which just happens to be different to the one that they are on. So the message can't get through to them, and it looks like they'll be stuck in Genoa for a while. And so it is with our transport networks. When we've got a problem, we must be able to send fault signalling back down the same route that the traffic is using. And that's why MPLS-TP does not support non-congruent paths. So MPLS-TP gives us confidence that we know for sure the route that our traffic is taking, and it's guaranteed that the reverse path is the same as the forward path. So in a phrase, we've got deterministic, congruent LSPs. Now, I said before there were 3 features of IP MPLS that must not be available in MPLS-TP. So let's take a quick look at why. So the first one was called penultimate hop popping. You'll remember that the egress LER has 2 jobs to do. First of all, to remove or pop the label, and then to route the packet. Well, PHP simply removes the label at the LSR just before the final LER, leaving the LER only the job of routing to do. The idea is that it improves efficiency, though some people doubt this. The problem for transport operators is that PHP assumes the payload is IP, and so for that reason alone, PHP cannot be a feature of MPLS-TP. And secondly, equal cost multipath. ECMP is all about load balancing, sharing the traffic flows over multiple routes which have the same cost. For the transport network operator, this approach removes the deterministic nature of the paths, and ECMP therefore cannot be a feature of MPLS-TP either. And the third of the unwelcome features in MPLS-TP is called label merge. There's actually a lot of efficiency logic in label merge. If packets on different paths but labelled in the same forwarding equivalence class arrive at a common LSR, then they are effectively combined by giving them both the same forwarding label number. However, there is a downside. As soon as paths are merged in this way, we're no longer able to uniquely track back to the origin. In other words, we lose source information, and the paths are not deterministic. And so label merge joins PHP and ECMP in the group of features not allowed in MPLS-TP. The great thing about IP MPLS is that it's the most powerful, efficient and effective technology for handling labelled routed paths in the core. But for access, aggregation, transport networks, we need the predictability and the resilience of MPLS-TP. Now, one vital aspect of managing a transport network is to have a toolbox of OAM functions. We need to be able to check the integrity of the network paths, and MPLS-TP gives us these connectivity verification tools. In MPLS, we have a model where we talk about 2 planes: the control plane, which is responsible for the dynamic establishing of the LSPs, and the data plane, which actually carries the fixed LSPs themselves. In MPLS-TP, the OAM functions are also handled in the data plane in an overhead channel called the generic associated channel, or GAC. Inside this channel is a virtual circuit used for connectivity verification, and that's called a VCCV. And this circuit is used to relay the verification tools such as ICMP ping, that's the standard ping we're familiar with, and then two new tools, the LSP ping and also BFD, that's bidirectional forwarding detection. And it's also used when required to carry performance monitoring data and also to relay protection switching information. Okay, let's have a look at a summary of LSP ping and BFD. LSP ping is actually a set of options that gives a comprehensive view of the network. And BFD, well, there are various variants of BFD, but essentially this tool is used for checking failure of the data plane, and if it is detected, it reports it very quickly, usually sub 15 milliseconds. Now let's look at path protection. Effective path protection has always been a vital element of transport networks like SDH, and so MPLS TP has adopted the same protection models. Let's take a quick look at the three types. 1+1 protection is based on having a dedicated protection path where the transmit signal is sent on both working and protecting paths. A failure in the working path causes a switch at the receive end. Switching times are very quick, sub 50 milliseconds. The 1-for-1 scheme is similar to 1+1, but here the protecting path only carries the transmit signal when there is a failure in the working path. When the working path is carrying the transmit signal, the protecting path is available to carry lower priority traffic. Then finally, the 1-for-N scheme. This is designed around a shared protecting path. Two or more working paths share a single path for use when one of the working paths fails. Relatively, this is the most efficient use of resources that provides a protection path, but it's clearly the one with the greatest risk as it can't handle the failure of two working paths. Okay, so how does MPLS TP implement these high-speed protection switchovers? Well, it uses a function called the continuity check, and it's one of the crucial fault monitoring tools we have because, as its name suggests, it's proactive. Continuity check messages, or CCMs, are repeatedly sent out as multicasts from each endpoint to peer endpoints, and they're sent every 3 milliseconds. If 3 or more expected incoming CCMs go missing, it can be assumed that there's some sort of line failure, and the situation can be reported within 10 milliseconds. The message is then processed, and an instruction can be sent to the switch selector to switch to a protecting path in a guaranteed switchover time of less than 50 milliseconds. So, with these classic circuit-oriented features being added to make MPLS TP a resilient carrier-grade technology, we now have the possibility of operators replacing whole SDH transport networks with MPLS TP. So, bringing this brief introduction to a close, what can we say about the benefits to the operator? Well, as with most things, it partially comes down to money, and there are many savings to be made. The setting up costs are relatively low. MPLS TP devices are cheap because they don't need all the complexity of routing capability. They're simpler to work with, so less training is required. They're more energy efficient, requiring smaller power supply systems. And because of the deterministic nature of the paths, MPLS TP is highly scalable. And the economies of scale are well known. And then there's the operational costs, and these are also lower. It's always the case when moving from an infrastructure based on older equipment. But there are also tremendous advantages when all the services that were carried by disparate traditional technologies are converged onto a single MPLS-based infrastructure, from its simplicity of network management to the elegance of connectivity verification. KeyMile is a leading worldwide manufacturer of carrier-class transport network systems. Keymile is ready to support your MPLS TP requirements and more with rugged, reliable, feature-rich platforms manufactured in Europe that will meet the needs of your mission-critical networks today and tomorrow. Keymile, because connectivity matters. Thank you for watching this key tutorial.